A clock on your head runs faster than the one at your feet, not by much but measurably with modern atomic clocks. Space itself curves, and that curvature steers every motion. That includes light, planets, and even your watch. The immediate takeaway is simple and weirdly practical. Gravity is geometry, not a mysterious pull from nowhere. The shape of space sets the path things consider straight. Your body, your phone, and starlight all obey that shape. Today we will see how that control plays out everywhere. Float in a quiet spacecraft and release a pen beside you. It drifts in a line, not caring about the ship's walls. That line is the straightest path the region allows. A geodesic is that straightest route through spacetime. Motion gets simpler when you switch from forces to shapes. Shapes replace pushes, and inertia becomes following the shape. Here is the working picture, kept brutally plain. Mass and energy bend spacetimes measuring sticks and clocks. Objects move forward in time while tracing that straightest route. It can look curved in space, yet stay straight in spacetime. Think of highways on a globe, bending on flat maps. Airlines use great circles, cutting hundreds of kilometers on crossings. Rule of thumb, straight means least effort by spacetime's yardstick. Coffee slides when your tray stops following a straight route. In orbit, you and the pen keep that direction together. Near stronger gravity, the yardstick changes faster across space. Paths that start parallel can converge or diverge without pushing. Net result motion is straightness judged by a curved arena. Starlight passing a galaxy cluster does not travel in a perfect line. It curves because the cluster reshapes the surrounding spacetime. Gravitational lensing is light following geodesics through curved space. It matters because lensing proves geometry controls even light's direction. The field does not tug photons like strings, it shapes their road. Closer to mass, the road tilts harder, so paths deflect more. When mass is symmetric, curved routes can merge into bright rings. Foreground clusters can split one galaxy into several stretched images. Here is a concrete case you can picture with numbers. The cluster Able 1689 bends light from far background galaxies. Hubble revealed arcs wrapping its core, magnified by factors of 10. Those arcs let astronomers map invisible mass by reconstructing the road. Einstein predicted this in 1915, then Eddington measured a solar version. Starlight near the sun appeared shifted during a total eclipse. The offset was tiny, about 1.7 arcseconds. Tiny test, yet it matched curved spacetime calculations exactly. Lensing now weighs galaxies, maps dark matter, and times expansion. One sentence recap, light obeys geometry, the same as stones. Open your Maps app and watch your position settle within meters. That accuracy depends on clocks racing overhead, ticking at different speeds. Gravitational time dilation means clocks deeper in gravity tick slower. Navigation breaks without correcting that bending of time. Satellites orbit higher where Earth's pull is weaker, so time runs faster. They also move quickly, which slows their time by special relativity. These two effects fight, but gravity's part wins at GPS altitude. Net speedup is about 45 microseconds each day per satellite. Engineers pre-offset each onboard clock so signals land correctly. Your receiver solves distances from light travel times using triliteration. Miss those offsets and locations drift kilometers within a day. Standing up even changes your rate by 1 part quadrillion. Laboratories measured that difference across centimeters with optical clocks. GPS satellites fly 20,000 kilometers above Earth's surface. They circle every 12 hours, near 4 kilometers per second. Each nanosecond of timing error equals 30 centimeters of range error. A few dozen nanoseconds can misplace you by city blocks. Engineers bake relativity into design instead of patching after launch. They tune clock rates on the ground and adjust them in orbit. One calm recap, time bends with gravity and devices must respect it. Stand on a cliff and throw a ball sideways hard. It arcs down because Earth curves beneath the thrown path. An orbit is just free fall while continuously missing the ground. That reframes gravity from a force to pure geometry. Here is the working picture without heavy math or jargon. Curved spacetime sets straight lines that bend through visible space. Launch fast enough and the straightest route clears Earth's surface. Slow a little and your path intersects mountains or oceans. The International Space Station shows the numbers cleanly. It moves at 7.76 kilometers per second. It falls toward Earth while Earth's surface falls away beneath. Drag from thin air robs energy, so regular reboosts are needed. moons follow the same logic, circling planets and dwarf planets. Rule of thumb, orbital speed falls with altitude around one body. Pick any altitude and there is one circular speed for staying. Gravity defines that speed through curvature steepness at altitude. So the picture is orbits are straight paths through bent spacetime. One sentence recap, orbiting is free fall, guided by geometry. Point a vintage telescope at Mercury and track its closest approach. The ellipse slowly rotates, beyond what Newton's gravity explains. General relativity fixes that rotation with curved spacetime near the Sun. That became the theory's first sharp, precision stress test. Another twist appears near spinning masses, named frame dragging. Space and time get pulled around like honey stirred by a spoon. The effect is tiny near Earth, yet measurable with gyroscopes. Gravity probe B watched onboard gyros drift, matching predictions closely. The geodetic precession was 6.60 arcseconds yearly. Frame dragging added about 0.039 arcseconds yearly. That is spacetime's subtle swirl, caused by Earth's rotation. Black holes spin much faster, making that dragging dramatic. Disks twist and jets align, steered by rotational geometry near horizons. LAGEOS satellites tracked nodal precession, using laser ranging. Their orbital planes shifted milliarcseconds per year, aligning with theory. Those shifts confirm Earth's spin gently twisting local spacetime. Bottom line, rotation does not just move matter, it drags space. Near a black hole, the straightest routes wrap like racetracks. Light can orbit at the photon sphere if aimed just right. An event horizon is where all future points inward. This matters since these objects expose geometry stripped of extras. Here is the mechanism, told by accretion and light. Gas falls inward, heats violently, and emits in X-rays and radio. Curvature there is extreme, so light paths swirl and delay. Some paths loop many times, boosting brightness into rings. The Event Horizon Telescope resolved a shadow from Sagittarius A star. Its apparent size is 50 microarcseconds across at 8 kiloparsecs. That matched mass estimates, confirming the geometry near the center. Frame dragging near spinning holes reshapes disks and aligns jets. Binaries inspiral faster, then merge with space-shaking waves. LIGO recorded chirps rising to hundreds of hertz before silence. The radiated energy equaled several suns, released in 1 second. Those waves are spacetime ripples, racing at light speed. They nudge mirrors by 1,000th of a proton's width. Bottom line, black holes reveal space-dominating motion in pure form. Zoom out to clusters and watch galaxies drift apart over time. Cosmic expansion means distances grow as space itself stretches. It matters because that growth sets large-scale motions and histories. No galaxies push outward, the metric between them increases. Each megaparsec adds recession speed, set by Hubble's constant. The present value is about 70 kilometers per second per megaparsec. Nearby galaxies can override this with local gravity pulling together. Andromeda approaches us now, near 110 kilometers per second. Farther out, expansion winds and recession speeds climb. Light from very distant galaxies is stretched red by this growth. Supernova surveys used that stretch to reveal accelerating expansion. Dark energy names the driver, still debated in active research. Baryon acoustic oscillations leave a ruler etched into galaxy patterns. Those ripples calibrate Hubble's curve across billions of years. One sentence recap on huge scales, space's growth steers traffic. Spin a galaxy in your head and watch its stars circle. Outer stars move faster than visible mass alone can explain. Dark matter is extra mass that bends space, yet barely interacts. It matters since this hidden mass sculpts every galaxy's structure. Halos of dark matter create deep gravitational wells around galaxies. Gas cools and settles inside, forming disks, bars, and spirals. Stars then follow geodesics set by the combined matter. Rotation curves stay flat with radius instead of dropping. In many galaxies, halos outweigh stars by factors around 10. Clusters reveal it starkly through lensing and galaxy velocities. The bullet cluster shows mass offset from hot gas after collision. Lensing maps place most mass with galaxies, not the shocked plasma. Simulations grow cosmic webs where halos feed filaments and nodes. Satellites stream inward, leaving tidal shells and elongated streams. For the Milky Way, stars orbit near 200 kilometers per second. One sentence recap, dark matter bends space and structures respond. Remember that faster head clock and the slower foot clock. That tiny difference is space telling time how to flow. The same language guides satellites, orbits, light, and black holes. Once you see motion as geometry, the universe snaps into focus. If you want more clear space stories, come subscribe for the next one. Thanks for watching and for giving your brain new geometry.